And while the last panel focused on long-term planning, our focus will be on real-time applications such as emergency response. And the expertise represented by this panel spans the fields of earthquakes, fires, air quality, and water resources. And by way of introduction, I'm Diane Evans, and I manage the Earth Science activities at JPL, where we're taking the lead from the decadal survey, the National Research Council decadal survey that you heard about this morning, and putting more emphasis on societal benefits, and hence our interest in today's symposium. So this includes not only our observational capabilities and scientific capabilities, but also our expertise in systems engineering. And I think you heard this morning about the importance of that so that we don't have unintended consequences of some of our actions. Next to me is Gerald Bawden from the U.S. Geological Survey, who studies mechanisms that drive natural and human-induced disasters, such as earthquakes and fires. And next to Gerald, we have Eileen McCauley, whose section at the California Air Resources Board is responsible for research in such diverse areas as atmospheric chemistry, climate change, global air pollution, model improvements, and instrument development, as well as emissions inventory improvement. And next to Eileen, we have Phil Riggan from the USDA Forest Service, who does research on remote measurements of wildfire properties, ecology of the effects of fires in Mediterranean-type ecosystems of California, and the global consequences of wildfire in tropical ecosystems. And finally, we have Sorooshian from the University of California, Irvine, whose area of expertise is hydrometeorology, water resource systems, and climate studies, and application of remote sensing to earth science problems with special focus on the hydrologic cycle and water resources issues related to climate. So with that, what we'll do is basically follow the same standards that were set up earlier today, and we'll give everybody about 5 minutes each to make their opening remarks, starting with Gerald.
Thank you. The USGS has a long history of working with real-time data as well as remote sensing. We go back with the USGS was charged with making the initial topographic maps for the United States. That is folded into doing digital elevation models, and then now we help distribute the SRTM data that was collected with NASA, as well as we've got a website called Click, where we're basically working on trying to distribute publicly available LiDAR data for all of the U.S. We are also are now running the Landsat continuity missions, and so discussed earlier today that basically it's bounced around. Hopefully it's in its final home, and we've got data with Landsat going back to the early 70s, and currently we're now offering all the data for free. There's no charge to the current Landsat data. You just go there, click on the area that you want, and you can go ahead and download it. And we're systematically working on going back in time so that we're able to have a more rich and robust time series analysis that can go ahead and come from it. So in the spirit of the session with kind of real time, when Diane initially proposed real time, so there are a lot of different applications, and the first one that comes to mind for me is basically hazards. That's part of where my research goes from. And that goes with everything from earthquake hazards, volcano hazards, land subsidence associated with groundwater pumping or karst collapsing. You got landslides. There are other real-time or near real-time applications. You've got glacial health, although you might not say that's initially real-time. There have been more and more studies saying that you've got some large glacial surges that actually, if you had a real-time system, would be best to monitor. You could also use satellite imagery for flood analysis, especially with the radar where it's cloud penetration. Kind of give you let's see. All right, we'll start with that. I want to get an animation going, kind of going with hazards. How stable is Southern California? We're looking at above our heads is a synthetic aperture radar interferometry image at the bottom, and in the right-hand corner is Landsat. We're flying up towards Los Angeles Basin, where groundwater pumping is causing the basin to rise and fall upwards of 6 centimeters a year. Newport Inglewood fault off here. Got Portuguese Bend landslide, off on the side. We're just across to a different radar scene where we're looking at the Northridge earthquake. So each of the repeating color bands, as Andrea described before, represents about 3 centimeters worth of distance change between the ground and the satellite. So just as we flew from San Diego up through here, we've seen tectonic, we've seen landslide, we've also seen groundwater. As our little Cessna flies up and over the Coast Range, we're going to come out into the area where we got Palmdale, got ag pumping out here, and we're seeing extensive groundwater subsidence up in this area. As we continue around the bend, we're heading up to close to the Mojave River, which is actually showing up as a line of incoherence. It's non-data. We'd actually map this area where the INSAR breaks down, and from that we're actually able to see which rivers were flowing during a given rainstorm event and which were not. As we head further out into the desert, we're seeing the fringes from the Hector Mine earthquake. We've had tens of meters worth of displacement, if I remember right. And now off into Coachella Valley, so Palm Springs is right over here. Basically, you could map land subsidence in the Coachella Valley by seeing, I could superimpose all the golf courses. Each golf course is dropping down, so it gives new meaning to the 19th hole. As we head out a little bit further, you got this little rhobohedral that's dropping down. That's a date farm. It's basically they're pumping water from dates, and it's a fault-bound system, and we're just seeing a fair amount of land subsidence. And we'll end it with geothermal subsidence up in the corner right up here. So this is just a quick little snapshot where we looked at just various INSAR scenes throughout Southern California for the last decade, and we've seen a lot of different types of deformation. So it's Southern California in general is a very dynamic place. Some of these areas we also overlooked showing hydrocarbon extraction where you see land subsidence. There's areas where we have aquifer storage and recovery where we actually have injection going in. So we're seeing uplift. So that is also a proxy for carbon sequestration. So the strength of what I just showed is basically we're able to, with remote sensing imagery, we're able to take huge snapshots, see so much that's going on. Some of the weaknesses, though, is basically we got all these repeated colors up there. So geeks like me need to be able to go ahead and synthesize this down to a point where the congressmen that we've had up here earlier to be able to go ahead and make informed decisions. And so far there's been more of a disconnect in being able to go ahead and take this type of science products and be able to work its way down. There's also, I'll just dealing with other applications that we could use with INSAR. We had the NSF-funded EarthScope, which is a huge solid Earth science initiative looking at a lot of different parts of the U.S. One of them was basically doing plate boundary observatory. About 1,000 continuous GPS receivers along the plate boundary looking at land, or basically looking at tectonic motion and the earthquake hazards associated with it. What we found is basically groundwater pumping is actually producing some of the largest deformation that we're seeing, especially in the Los Angeles basin. So I chaired the site selection committee. We used INSAR for siting almost all the PBO sites in California. So what we did by doing processing the INSAR, we found out where you had groundwater and hydrocarbon production. We either placed the GPS sites right in the center or outside of those areas. In the center, the GPS data then will be able to be used by hydrologists as well as tectonics. There's also an issue of, I'll just say, scalability. What makes the fusion of GPS and INSAR so meaningful is the fact that GPS, we're able to get daily time series, or actually, with the high rate, we're able to get 1 second time series. With INSAR, you're able to go ahead and look at the full spectrum, the full area, the spatial. So when we think of remote sensing, we actually should be looking at both the spot calibrations and the timing, as well as the spatial distribution of the deformation. We could also take this down from size. I just showed all of Southern California. Now what I'd like to do is use something ground-based LiDAR. It's a handheld system. I'm able to take 0.1 millimeter spot spacing if I want to. And so go ahead and start this animation here. We're looking at a time series collected. Oops, actually, could you begin this at the beginning? Take the slider. Just.
A lot of real estate here.
So with the scalability, the LiDAR, you're able to go ahead and come in with ultra-high resolution. What we're supposed to do is actually show a Google Earth image of us flying from here down to Laguna Beach, and then from there, we'd be able to take a closer look. Okay. My apologies to Brian of Google. Now what we're able to do is start integrating airborne sensors, satellite sensors, within ultra-high resolution detail. So what we're looking at is the deformation in the days that followed the Laguna Beach landslide. I went out there, generated time series, really trying to look at the displacement, trying to understand had the landslide did its job or was there still continued motion. The other thing with this is visualization. I'm an adjunct faculty at the University of California, Davis, where they've got the Keck Caves. And what it is, it's a room that you're able to go into and put on goggles and see this data in full 3D. And so I think part of the essence of trying to communicate our science outward is be able to come up with better visualization tools to be able to make this data meaningful to a larger audience. I could go on, but I'll end there.
Okay, thanks. Okay, Eileen?
Okay. Chairman Nichols, I think, did a good job of giving an overview of ARB's interests. I will start with some very, I think, traditional satellite photos. Okay. I'd be surprised if anyone in the room hasn't seen this sort of photo. It clearly uses satellite data, OMI data, to identify a hotspot in Asia. This is a sort of global perspective that we're all familiar with, that satellites have been very, very successful at adding to our information. Next slide, please. But the title of the seminar is California. Okay, this is California. It's Omni data. It's NO2 data, and if you look at it, you see what you expect. NO2 is largely produced by mobile sources, so the Los Angeles area, Southern California, is quite red, as is the Bay Area and down the Central Valley. No surprise there. Next slide. But we need better resolution. The Air Resources Board has a very fine-scale interest. We're interested in people's exposure, in modeling people's exposure. So we need finer resolution. I think that's the last slide. What we'd like to do, back up one slide, please, is on the upper left for you, you see satellite data. On the upper right is Landsat data, which shows you the topographical features. We would like to resolve that emissions data with finer detail so that we can start to see the impact of some of these topographical features. And then the bottom one is our emissions inventory. Okay, modeled data. So this gives you an idea of the scale that we're interested in, because we're interested in people's exposure, and that's going to vary dramatically. Last slide. This is to give you something to aim for. We would like to identify, ideally, wouldn't it be wonderful if we could have real-time data about specific sources, about freeways, point sources. I realize that's a ways in the difference, but that would be an interesting place to go. Something that AB 32, the climate change focus, has brought to ARB that's new is an interest in land use and albedo. Okay? Those were something that we hadn't paid a lot of attention to, but those are an area where I think satellites can be very useful. Land use has very important implications, not only for climate, but for transportation, for energy use. Albedo, reflectivity. Earlier today, someone mentioned Dr. Chu's interest and Dr. Rosenfeld's interest in increasing urban albedo to not only decrease the urban heat island effect, but possibly to even help counteract some warming on the surface. Well, if we want to be quantitative about this, we need data. It isn't enough to say white is good and leave it at that. That means we'll need albedo measurements. So satellites can be very valuable to the air quality regulating community, not only in the traditional chemical measurements, which we have found useful and will continue to find useful, but in ever-increasing ways. One thing, though, that I think, and we'll talk about this during the panel, is how can we make sure this data is used by more people because it is such a rich data set. And I think that work needs to be done in that area, making the data easily accessible, making software available so that the average person at a local agency could use the data. Google Earth is just phenomenal. You know, the average person can get on Google Earth and start using it fairly quickly and really learn a lot. Wouldn't it be wonderful if satellite data were that user-friendly? Then you could have people at local agencies starting to use it. And I think we'll discuss that more during the panel.
Thanks a lot. Okay, Bill?
And have the first slide, please.
While we're waiting for that, let's see, are there cards that are going to get, so Michelle's going to, same as this morning, we'll send around cards, and if you could fill those out, and they'll be collected, and Mike Gunson, again, will look through those and pass those along to us.
You're looking at one of our images from the Firemapper, which is a specialized thermal imaging radiometer that the Forest Service has developed with a small company called Space Instruments down in San Diego. Firemapper was one of the early civilian uses of a microbolometer focal plane array. It was remarkable in that we were using an uncooled system to make measurements in the thermal infrared. The Forest Service has been flying the Firemapper on fires now since about year 2000 in Southern California. We've developed the imager and have been conducting research to learn more about fire and its role in the environment. The thing about doing research with an imager is that it turns out we know a lot more about what's going on with that wildfire than the folks that are doing the hard work down on the ground. Traditionally, the Forest Service and, in fact, the federal agencies have used the National Infrared Operations Program, which comes out of Utah. Have 2 aircraft, use line scanners, and fly typically in the early evening hours, providing a map of fire location, basically a perimeter, by the 6 a.m. briefing of the incident team the next morning. In Southern California, that misses a whole lot of the very interesting action, and anyone that has been in Los Angeles for the last 2 weeks understands the problem fully. Now, what's the situation like for the firefighters on the ground? Just as a couple of examples, I asked a friend of mine, Battalion Chief Don Pierpont, who's now retired with LA County Fire Department, what he was doing back in 1993 on the Green Meadow Fire. He said that he was with his driver in his car trying to stay ahead of the fire as it was burning through the Santa Monica Mountains so they would know where the head of the fire was. In 2003, I asked the early incident commander on the Cedar Fire in San Diego how they knew the location of the fire early on. Well, they didn't. They could see the glow over the hills. It was in a very dangerous location. They worked for about 4 or 5 hours to try and find out where the fire was located. They couldn't get to it. The Santa Ana winds surfaced, and the fire took off for San Diego. So I said, wow, so what time did it hit San Diego Country Estates? Well, that was sometime around midnight, 1 a.m. When did you know it was going past Highway 67 in Ramona? Well, I went out there with my driver, and we went down the highway, and it had already gone past. So that, unfortunately, is the state of affairs in incident command on fast-moving fires in Southern California. Now, we saw this morning imagery from the Icona. It's a line scanner that's flown out of NASA Ames Research Center. I've worked with the fellows there since the early 1980s to develop systems to make the right fire measurements. They're flying on the Icona most recently. We'll be flying on a King Air aircraft coming up. I use Piper Navajo. It's stationed here in Southern California. Another example of where things are headed now with airborne work, we now have 2 systems that are available in research and partly in operations that will actually make the right measurements on a fire. The image we're looking at is from the old fire in 2003. It was a Santa Ana-backed fire. This is about, I think, a couple, 3 flight lines where the data were rectified, mosaiced, and color-coded according to surface temperatures, as indicated in the long wave thermal infrared. You can see the fire is on the top burning up into the mountains, into the San Bernardino Mountains. By the way, we've overlaid it on a pre-fire image. You can see the fire burning down into a spreading ground here. And over the next hour and a half, we made about 20 passes over this fire and watched as it burned down into the city of San Bernardino. It went about 10 to 15 blocks into the city in various places, and you had fire burning from one residence to the next as it went in. Can I have the next slide? This is the Esperanza fire in 2006, which was very unfortunate. It was burning in the Banning Pass area, started in the early morning hours, and again a Santa Ana wind pushed it from the upper right down towards the lower left on the top image. Top image is our Firemapper data, colored according to surface temperatures. In this occasion, we were able to use a Global Star satellite communication system, orthorectify the data, put it out on the internet so the public could have access to it, or whomever was on the incident management team, using Google Earth, using shape files so that the data can be readily imported into the incident team's GIS mapping system, and so forth. And the team was actually using our data to know where the fire was and respond in the allocation of resources. It's probably the first time that we'd been able to do that in close to real time, and we were providing data that was about 45 minutes old on a 40,000-acre fire. I did want to show that there is a problem with resolution. On the upper slide, you can see a lot of detail in exactly where the fire is making runs with the wind. You can see gradients within the fire zone that tells you something about the amount of biomass that's being consumed, environmental impacts, but really idea of rate of spread and where the fire is very active. On the bottom half is a MODIS image from 3 of the half-kilometer channels. And it's basically the same period in time. So you get an idea that there's a lot more information in the high-resolution data that we collect from an aircraft. The MODIS has been very useful. Primarily, the best use, I should say, that I'd heard is from Dr. Frost down at San Diego State, who was using the MODIS, making the data available to the public, and where you had 1 or 2 million people that were being evacuated from the city in 2003. A lot of folks didn't know where the fire was, and if you told them the fire was near Ramona, they had no idea where that was because they're urban dwellers. And so the MODIS was very useful in helping the public to understand the magnitude of the situation. And I think any of you that have been here recently probably suffered from the lack of information on the station fire as to knowing exactly where it is and how fast it's moving. So I think it's very important for us to try and take especially the high-resolution data, make it more readily available, move it out in forms that can be used by the incident command teams, but also make it available for the public. And just to conclude my remark, I'd like to point out that we're going to have the big one here in Los Angeles someday, and these fires are going to look really small compared to the disaster that could hit when that drill we just had on earthquake preparedness turns into reality. And you're going to see fires at the same time you see bridges collapsed and millions of people trying to evacuate an area. How are the emergency services going to know in real time where the bridges are collapsed, where the fires are, where people are most threatened, where the clear routes might be to move through the city? I think we really should be considering how we can take existing resources that may be military, but I think should be civilian, that are in research or in a semi-operational mode, and coordinate those so that when we have this big problem, we can respond to it. I have one more I have to just mention, and that is, and if you think that fire was a problem, and we actually have an El Nino, wait till you see the debris flows. Now, when the last time they had a really big fire in the La Crescenta, La Cañada area, there were boulders the size of trucks going through the streets. Now, that was before the advent of flood control basins. In 1979, the Rubio Canyon fire above Pasadena burned a pretty good chunk of the watershed, nothing near what we just burned. And the Rubio Canyon basin filled up, and they had dump trucks running day and night for 6 months trying to keep that debris basin cleaned out, and it still topped over 3 times, and you had sediment going through folks' living rooms. So we have a serious problem. We need to do a better job of moving real-time information for the people of Southern California.
Thanks. Soroosh?
Thank you, Diane. It's always intimidating to be invited to give a talk at one of the top 5 universities in the country, and it's even more intimidating being next to JPL, where all the talents are. So anyhow, and more so, having to give a talk by looking upward is a little difficult. So I'm gonna break away from protocol, Diane. If you don't mind, I stand up because I have a little neck problem. Excuse me. Anyhow, as Diane introduced, sorry. Well,
we need you to speak into a microphone.
Oh, to microphone. Okay. Well, then I will sit. Okay. No, that's okay. As Diane mentioned, I do come from the hydrologic community and water resources. And when it comes to planning and decision making, and of course the theme of this particular session is real-time and actionable items which really affect people. So you're really talking about a whole spectrum of scales, going from river basins such as Mississippi River Basin, where some large-scale planning happens, eventually to, if you look at the lower map, there are almost 4,000 watersheds in the U.S. that are represented in this one. So that's where people live, where little communities are, and a lot of decisions have to be made, and planning has to take place at those particular levels. So decisions and real-time information has to be put in the context of the scale by which we have to look at it. Next, please. And in this particular diagram, it shows the spectrum of the type of hydrometeorological, essentially information that one needs. And when we talk about real time, the focus is going to be more within the hours to days, and that's the context of floods and flash floods. And the rest of the picture that you see represents mid-range forecasting and long-term forecasting, that some of those were alluded earlier in the earlier session. So I'm going to try to focus on really the short term, where maybe remote sensing will play a critical role. Next, please. Well, floods are nothing new, particularly in the southwest U.S. The only thing that is important to realize is that one of the consequences of global warming has been identified as being the intensification of the hydrologic cycle. And if you look at the past 100 years of instrumental records put together by NCDC, you will see that on the average amount of precipitation over the continental U.S. has increased by 6%. But the number, or the percentage of extreme events, particularly extreme precipitation, has increased by 20%. So as such, we are most likely may not see as much rain, but when we do see them, they're going to be much more devastating, and unfortunately, with respect to this year, as Phil mentioned, it would certainly create many challenges. Next, please. So really, if you think of those time scales from the hydrologic and water resources point of view, there is nothing more important and nothing more challenging than the estimation of precipitation, rainfall, at the resolutions, time and scale that actually would be of value to resolve, for instance, a thunderstorm like the one you see over Tucson, Arizona, where I used to live, and I took that picture, and you see how dense they could be, and flash floods could be pretty serious as a result of these storms. Next. So what are our choices as far as observations goes? We have rain gauges. We have a Doppler radar system that has been deployed over the U.S., run by the U.S. National Weather Service. And by the way, there are 13 river forecast centers that cover the U.S. that are responsible for providing flood forecasts, etc. And then most recently, there have been quite a better emphasis on the satellites. The big question when it comes to operational at the scales we're talking about is that which one of these do you trust? And maybe none of them are trustable. The question is what combination, how do you make the information to be valuable to the decision makers and the users? Next, please. So on the right-hand side, is a representation of the official locations where the rainfall gauges in the western United States exist. While you might see it to be pretty dense, you say, well, that's pretty good coverage, but please read the text at the bottom. It says, daily precipitation gauges, it's roughly about one station per 600 kilometers square for the Colorado River Basin. And as we get to the more mountainous regions, there's less gauges because obviously it's more difficult to install those. And when you get into hourly and shorter time scales, the situation is even worse. We rely a little bit more on the radar, and I don't know if you noticed, it went through a couple of animations. It started from 3-kilometer angle of observation for the radar down to 2 kilometer, down to 1 kilometer. And western United States, the Doppler radar actually has a hard time to see anything because of the abstractions of the mountains. So you don't really necessarily get much coverage. Which brings me to the point, next please, is that we are fortunate to have a lot of environmental observations, particularly geostationaries, and now a good number of microwave. And the question has always challenged folks in the satellite algorithm side as well as application and user side, is that how can we combine these things to actually use space-based observations to fill the gaps and provide real-time precipitation information. Next. There are a good number of groups that are actually producing the information. I'm putting the website of Goddard only because Jack is here. That's been something that has been really a flagship with the Tropical Rain Measuring Mission. It provides a 25-kilometer resolution, a series of products, and I encourage you to look at it. And then, of course, what would the talk be without talking about our own stuff, which is the next slide. And our group has been involved with also satellite precipitation. But if you wish to see the difference with our group versus others, they've come from the climate community trying to make the data useful for the climate applications, where we have come down from bottom up, more from the hydrologic side, to see at what scale and what resolutions data could be useful. And there are a number of things that are appearing on our website that I can't go into much detail, but pretty nice features. And we are now producing with the cooperation with UNESCO, because UNESCO certainly has a vested interest in that kind of information for water resources applications globally. And then we have a 4-kilometer resolution precipitation, almost near real time at 30-minute accumulations that gets updated. Next, please. And yes, we also have a KMZ file for the Google, which is really pretty popular, particularly from our international communities. As they go to our website, they can actually superimpose this, and there is a weather component of the Google Earth, and they can actually superimpose it with the clouds and see what's going on. The next one is that, well, at the end of the day, it's what are you providing to the users and how do you buy their confidence when it comes to applications. Just a case in point, the devils are in details. Here is radar versus a well-gauged watershed in Arizona. And the whole point of this is that even at that scale, with a lot of work that has been done, there are many times where you see that the two are not necessarily compatible. In this case, gauges are very accurate, but the radar was overestimating almost by 70%. So we see that a lot. Then when you try to bring the satellites into the mix, the question is how bad or how good or how can we really improve the situation. Could you go to the next one, which I think is perhaps the last. There have been some limited studies done and actually comparisons made between the three different sources of information. Of course, there's more I couldn't include that are a combination of. So as you see, I think satellite products are not disrespectable. They're pretty good as far as compared to the others. Maybe not as perfect, but still they're doing a good job of at least capturing the ups and downs, and I'm sure as improvements come, they will improve more. Next. This morning there was a lot of talk about the longer-term requirements. Anytime you actually have data for near real time, that data could be a potential gold mine for even longer time. This is 2 climate models, and I think Barry and others, quite a few people mentioned. They're not necessarily perfect, and these are 2 models, and one of them points that the trends of precipitation for the western United States is likely to be on the increase for the next 20 years, where the other one shows that that actually is going to be on a decrease. So how do you really actually use that information? And the only way that I can say is that hopefully with more information and the data we have about precipitation, the type of studies that Steve mentioned, retrospective studies, could actually force the modelers to stand their forecasts or predictions against what actually observations tell you. But without high-resolution data, you probably cannot really accomplish that. I think that was the last one.
Thanks. Okay, so let's spend a couple minutes discussing a couple things, and then we'll take your questions from the audience. And I'd like to start maybe with Gerald, because you mentioned to use your word, the need for geeks to communicate better with decision makers. So let's investigate as a group, what are the real impediments and what can be done to improve the situation?
I see a number of different issues here with being able to take scientific data and convert it into products that could be used by decision makers. One is we've got to find out what products are really needed. What products can you use at what time? We just mentioned basically this fall we're going to have debris flow hazards for basically the whole station fire. And some of the preliminary debris flow hazards estimates we're still the USGS is still working on, but it looks like it's going to be the same level that it was actually for the Olden Grand Prix fire. So the ones that produced the Waterman Canyon and the Greenwood Avenue debris flows. And it looks like you could have debris flows that initiate within just a typical 2-year rain event. So, but as scientists, basically, we're looking at probability. How do you go ahead and take the probability into having products that the decision makers need to know, when do I go ahead and evacuate people? And I think this is where there still needs to be more work trying to bridge the gap between there. Because we could say statistically there's this probability of having a debris flow based on this type of rain. And I think being able to go ahead and have, using the debris flow as an example, having more ground-based sensors out there, having more forward models. So basically, if we have a storm coming in, a Pineapple Express storm, where's the rainfall going to come from? Where are you going to have the longest distribution or the intensity? So you need basically rain gauges. You need to have higher, better quality SmartR radar trucks to be able to try to map it, therefore be able to then start integrating that in near real time into being able to say this hill slope here is more susceptible to failing than other slopes. So we go ahead and take that example, we could expand it elsewhere. We also have basically synthesizing the imagery itself. INSAR, it's an incredible technology. We're able to look at sometimes sub-millimeter range changes from space under most optimal conditions. But we as scientists, we tend to keep things in the radar where we got these repeated color bands instead of going ahead and reducing them out. Whenever I downscale it, you lose the detail. And so that's why I tend to keep things in the repeated color patterns. But that's not what other people need. So there has to be a better way of working on visualizing some of the scientific outproducts that can actually be easily brought up and used at for the informed decision makers. The other thing I think is also data latency. My group was part of the International Charter. It's a collection of international space agencies that go ahead and have agreed to go ahead and turn on satellites for different natural disasters. The USGS were one of the participating, as is NASA. And within the USGS, there are 3 distribution centers. Mine's one of them. And my group handled all the data for the 2007 firestorm that came down through. There was that wreaked havoc here. And so here's imagery that's basically supposed to be used for informed decision makers. It took us 32 hours to download one image from the Japanese Space Agency. We had others from Indian space agencies that would take hours. I've had a high-speed connection, so basically getting bandwidth to be able to get the data down, and then coming up with, I'll just say, common distribution nodes, being able to just get the data out so that basically there's one-stop shopping, or if you need one type of imagery, go to this area, go to just a couple, instead of basically having all these hidden websites which people need to go to.
Good point. Okay, changing pace a little bit, and maybe we'll come back to some other. Did somebody else have some comments on that? Phil, you probably do.
Yeah. Google Earth has been terrific. We've been showing our fire data on Google Earth for a long time. And, I fly in the aircraft. I see thermal data and a whole bunch of smoke. And when I get back and finally see it on Google Earth, as do the incident commander and the fire behavior analyst and so on the incident, they can see, gee, the thing is actually over on the other side of the ridge, or it's across the riparian area now. They can rotate it around and see it in 3 dimensions. That's the best thing since sliced bread. You have to have something, though, that you're depicting that is just as intuitive as could be. So, we've basically taken a particular color scheme that should look intuitive. You think about glowing embers as being relatively hot, but not as hot as flames. Flames get up into orange and yellow and so on. So you try and make it very intuitive. You try and give a small amount of explanation. And it may take a little bit of training to interpret it, but that consistency in depiction is vital. We've seen other fire products that have come in that have been multispectral, and one time you get one color scheme, and another you get another color scheme, and I'm probably fairly expert on interpreting fire data, and if I can't tell where the fire is, we've got problems. So we need to have that kind of consistency, and it shouldn't be that difficult to get the few folks that are in the field together to talk about consistency in depictions. But it's really important. And the folks that are going to be responding in a disaster, if it's debris flows, it will be debris flows coming up, are going to need to have information, and it's going to have to be something they can put their hands on right now with no download time. It needs to be something that they've already seen, they know how to interpret it, what to do with it. And we had 3 workshops that were sponsored by NASA on fire remote sensing, on a variety of issues dealing with the post-fire environment, and then fire research after the 2007 fires. And I'm not sure what has come of it, but I know there were a lot of really good ideas. The first workshop was here at Caltech, and we're right back into it again, only this time we've got a few weeks before it all breaks loose. And it sure would be nice if we could maybe revisit what was learned at the last symposium and see if we can get some movement.
Oh, that's an extremely good point, because there's really no excuse for missing out on this one. One of the things, I think Andrea mentioned it this morning, of course, is the issue that NASA and a lot of the work that's being done is in the research mode. And so, for example, potentially some of these aircraft will be off doing their research activities right when we need them the most to be doing something that might be a little more near-term importance. And so any ideas on how we might be able to tackle that particular conflict?
Well, I missed the last fire because my aircraft was in maintenance, and they were not able to do something up at Ames either because they were putting instruments on a new aircraft. But there are 3 or 4 different possibilities, and so we all ought to be talking to each other in my small field to know what the state of the aircraft is. And we end up in the fire services having 2 or 3 people within the state of California that are typically involved in fire remote sensing, and they just pick up the phone and go down through the list. We also have a resource ordering system within the fire services for everything from fire crews to infrared and so forth, and we're in the list. So the dispatch center, which is interagency and located in Riverside, knows the status of all the different resources. So it would be important to make sure, especially for Southern California, that NASA resources or from other agencies are in the resource ordering system, and that everyone knows how to get a hold of them and move them. So there is a coordination system in existence, and we should make sure that the scientific talent can be.
I think the right person just took a note of that, so that's a good sign. Yes, please.
I think if I understood the question correctly, coming from an academic environment, and sometimes, particularly in the hydrologic sciences, going from basic research and science to operational really does require some special attention. Jack and I were talking about this some months ago. Unfortunately, it is not always that clear that there is enough time given for some of these products to actually mature to a point where you can buy the confidence of the users to start to use them. Okay, most projects may run about 3 to 5 years, but any time you go transition from research to operation, it actually does require time. It requires commitment, and to finally get the buy-in from the agencies and users to use them. As long as you have room to give them room to doubt about the quality of the data, they're unwilling to change.
That sort of fits in with what people are saying, but I'd like to suggest broader definitions or broader ways of thinking of two phrases we've heard today. One is decision makers. And it's been treated as if we're talking about perhaps talking to an assembly person or a single person. But many of the governmental agencies have staff. And if you think of these people as sort of support decision makers, so how do we get this data so that the agencies use it, so that the staff are more comfortable with using it? I think that's something very important to think about, not just making a presentation to an assembly person. Another question I think is interesting to think about, what do you mean by real time? Okay, in the air quality modeling arena, what we would love to have is, as we run our models for, say, an episode that happened a couple of years ago, if we could then say, we'd like all the satellite data for Saturday, August 12th. You know, if it were easy to access historical data, that's real time, because it allows us to go back and use that to improve our models. So I would say we would benefit from thinking about both real time and decision maker in a much broader sense, and there will be more use for this data.
Really good points. Yeah. Any follow-up on that? I think those are excellent points about in terms of working with the staffs, and so maybe that's a thing we can also follow up on, is, you know, that kind of a contact list as well. Okay, so we did have the question here of, well, what does real time mean in your context? And I think Eileen did a good job of in her area. Anybody else want to field that question? What does real time mean to you?
For my understanding of real time, it's really sensor dependent or platform dependent. Some satellites, if you're working with some of the Japanese or some of the satellites, they store things on board. So they'll collect the data. Then the next time over, it'll go ahead and download. So you've got a latency there. But I also think there's ways of trying to get around some of these lower latency issues, is basically trying to build constellations of satellites. So if we have Destiny, assuming it's able to get up, you're able to go ahead and have maybe 4-day repeat times with that particular satellite. And if we got 2 or 3 satellites up there in a constellation, then we'll be able to go ahead and reprogram the satellites on a quicker basis. So I think looking down the road, real time will become something where you have much lower latency. But right now it's really sensor dependent, and it's also often bandwidth dependent.
Yeah.
I think it's pretty much application dependent. I guess the notion of real time. There are cases where if you're dealing with issues such as flash floods, you're talking about minutes, tens of minutes, because some of those events come within about 2 hours. They have come and gone and have done a lot of destructions. So that's quite different than when you're talking about general floods, that even you have a little bit more leisurely opportunity to process the data. And then when it comes to snow, as important as it is, but at least it comes in a solid form, and you can actually process the data. You have a little bit more time to get the observations adjusted and corrected, and the only time then real time becomes an issue is when the melt starts. So all I want to say is that very much it's hard question to universally answer. It's very much application dependent.
Okay, good point. Okay, how about we talked this morning about really sobering facts about the loss of capability within California in terms of education. How should higher education and professional training be modified to create remote sensing savvy people who can use the data better in these efforts in the future? Any ideas?
Well,
go ahead.
You want to go, Phil?
Go ahead.
Yeah. Obviously, that again, maybe technology is really outperforming everything else. From one year to the next, capabilities have gone up, but the training program that you bring up people with the proper expertise to really manage the information and data may take a little longer. The question is, are the universities really responding to these? Yes and no. There are a lot of programs that are gearing up towards educating people. It requires a lot more interdisciplinary than the time I went to school. You have to understand many different fields, and whether the programs are responding to that is one thing. The other one is to get the students to be interested pursuing these areas. So, we find from time to time many challenges. But I think in general, I'm an optimist, and I think we are moving in the right direction, maybe not as fast as technology is actually moving. So,
I think that's a good point about the technology changing. And in my particular field, I think it's going to become less important to have highly educated folks that know how to do GIS that are on an incident team, because we're going to do a much better job of using automated processing to take the hard work out of it and present them with something that's more intuitive. And I think the trick there is you do need training for people, but the trick is to know more about what the first responder's job is and understand what their information needs are, and then work hard to make sure that that is delivered in a timely manner and without them having to do any work. I've had this experience numerous times in the Forest Service that you think, they could use this imagery to map out beetle kill up in the San Bernardino Mountains with all these dead trees. And sure, they have GIS specialists, but they're so busy that even if you give them data, they can't process it. So you give them processed data, and they don't use it. So you give them thematic maps, and they don't use it. So you put the thematic maps in Google Earth, and they use it. But there's no ability. It's not just state government that's been cut back over the last few years.
Well, I agree with you, Phil, on this. But at the same time, that doesn't take away from the individuals who use the information. I don't care how automated it becomes. They have to have the understanding and the knowledge. Case in point, recently I saw a presentation that projected a global map of all the landslide-prone areas globally. And I happen to have been born and raised in one of the countries that was honorably mentioned this morning, Iran. And I was really amazed to see a remote sensing product that showed the entire Iranian plateau to fall in the category of high risk, the whole entire country, high risk for landslides. And these are, you're talking the huge deserts, which I don't think there is much slope there for any kind of slide. But anyhow, that's a matter of people at least understanding the geography, or at least comparing it with the three-dimensional topography map, to not put stuff like that out, because once it gets out there, well, it's a little dangerous. So.
Yeah, well, you talked about getting the GIS experts on the incident team so that you could put that information out, and then we also had the conversation this morning about getting data out to the public. And I think any of us who were evacuees a couple weeks ago, we really appreciated the information that was out there. We were all riveted to the internet and our Google map, but it was pretty inaccurate. And it wasn't updated very much. And so it seems like, again, maybe having more people who had the capability, because it is all a matter of how many people have time to do this extra stuff. Maybe we just need more more people who are capable of updating maps with relevant information.
Another point there is that the agencies have to agree that the public has a right to know. And so there's an ongoing argument as to whether this needs to be vetted. We should give it out right away. Do we want to show, even though we have real-time video, do we want to make it available to the public? Oh, we might show their house burning. Well, boy, I've seen a lot of folks that wanted to know if their house had just burned, and 3 days later they're really agonizing over it, and just knowing would be better. But that's an ongoing discussion. And I don't think there's necessarily policy in the different agencies on this, but it's important. If people think they have that need and right to know, they should let the policy makers know that.
Yeah,
one other thing I'd like to add is that the data needs to be more easily accessible. I talked to a number of staff at ARB. I wanted to get a sense of how much satellite data was used, of what use it was. And from highly technical, very smart staff, they said, it's very hard to get data. It's obscure. It can be, people sometimes just give up. So if we want particularly students to use the data, it has to be something they can easily get a hold of.
Yeah, I was going to add on to kind of the concept of the right to know. It's like, does the public have the right to know? With USGS, we've got an incredible surface water program. We've got stream gauges all over. And we're developing different routines, being able to say, okay, if we've got a stream gauge here and your home is over there, will your home be flooded? And we've got, so you basically are using different scientific routines, analysis, and stuff. And so what happens if we say their home's not going to be flooded and something else happens within the process? Then do we become liable as an agency along these lines? And that's stuff that we have a lot of internal heated discussion with, trying to sort out what do we go ahead and convey out to the public and what do they need to know based on our models.
Sounds like add that to our list of impediments, I guess. Okay, so we have some questions that people have written, and so one of them is, from your experience, how do science and application pilot studies successfully end up as operational elements of response agencies?
How do pilot studies?
Yeah, when people do...
With enough patience to allow them to mature, not to really push for fast and quick products, because that could actually backfire if it's not matured enough.
So they need to be sustained
Absolutely
more than
sustained.
just
Absolutely.
Standard 3-year research programs.
Exactly.
Any additions to that one?
I think that you see a whole variety of folks in the agencies that might need data. And you were saying that we need to ask what is needed. But if you're talking to someone who's only seen a black and white television that's about this big around, they won't have dreamed of that beautiful flat panel in high definition color. And so what I found is that there's a wide variety of folks, and you have some that are very technologically literate and others that you would like to see retire. And that's not an age thing, you understand, but you tend to work with the folks that are very technologically literate, and they're the ones that are going to move things and take those pilot studies and put them into operation, because they're hungering for good information to do their job well, and so that's who you have to look for.
Yeah, and it's also often difficult, at least I'll just say within the USGS structure, you could go ahead and have brilliant ideas and be able to have them come through with a successful pilot project. But then the next part is being able to go ahead and convince the upper senior management that this is a tool that we need to be doing and using. And so now what you do is you basically take a scientist and put them into more of a politician's role, basically trying to go ahead and lobby internal and external to go ahead and get the support. And frankly, most scientists it's not their strong point. They've got the innovative ideas, and being able to actually take it to that next step further takes up much more than what their experiences are.
We touched on this, but maybe this is an appropriate one to just revisit. Are we preparing students with the right teaching, and are they immediate resource for interpretation and manipulation of data? and also then, maybe the next step is to convince people that that's what needs to be done.
Well, you have to ask the deans these questions. This is a bad year. With all the budget cuts, I'm not so sure if you're going to be. But kidding aside, I think programs are responding. I mean, as the need grows, obviously there is more emphasis being placed on bringing together a variety of these areas. Of course, you always are challenged if you don't have the right departments or critical mass of faculty, then how do you bring that knowledge to the students? And I think this could potentially be an issue, especially at the time when there are not enough resources. But then there are ways around these things, such as at least universities try to partner. There is a lot that can be done by web-based teaching. So I think, but again, it takes investment. With meager resources, you cannot really develop these kinds of courses and programs.
And I think what it takes is investment of time and mentoring, because as you said, often these students are extremely bright when it comes to manipulating computer code, but they're young enough that they don't really have sort of the real-world exposure, and that comes from interacting with a mentor who will look at their products, talk to them, pull sort of into their field of vision things that they may not have been exposed to.
Oh, that's a really good point. Let's see. Somebody was asking the question about using satellite observations for real-time events, given that most satellite data is over specific locations or once a day or once a week.
Well, when it comes to let's say precipitation or rainfall, the nice thing is that quite a bit of development has taken place based on geostationary satellites. Now, with the microwave, of course, being closer, you have snapshots much more accurately. And I think a lot of the algorithms are now trying to combine these things to give global estimates. As I said, our work is really at 30 minutes gets updated, so it's doable.
And I think we also heard compelling case for the role of aircraft sensors. So maybe that could be maybe that could also be beefed up.
Mm-hmm.
As well as having constellations of satellites.
Right.
Instead of just having one system, have multiple systems.
Okay. And then when, as these proliferate, though, is there a central clearinghouse or index that is available for local and state decision makers? What can be done to better disseminate scientific resources to these policymakers? I think we've touched on that a little bit, but let's have another visit of it.
Well, that's $1 million question for somebody who is not in the government agencies. It's easy for us to say, but I recall having chaired an academy panel not too long ago on the Advanced Hydrologic Prediction System. All the other government agencies were present to support the National Weather Service with their cause, but when our panel asked, I won't mention which agency, that you use the same kind of technologies and models, are you willing to switch to what this particular program at the end will produce? He said no, because our needs are special, et cetera, so therefore if we're talking about the modeling side of it, that there is a little bit of resistance, then the data attempts have been made, right? Jack, if I'm not wrong, there have been, at least on the global change, there have been master directories, etc. But at the end, people like to go to certain places to cherry pick what they need. So I think it will be a while before we really come to converge to just one place shopping for data.
Yeah, I don't think it necessarily needs to be one-spot shopping. I think what you need to do is get collections together of groups, and for instance, with the Plate Boundary Observatory, there's 1,000 continuous GPS sites. You've got a couple different groups that go ahead, process the GPS results, and then you've got a third group that basically combines them for a uniform approach. So basically, it kind of acts as a moderator between the competing software types, so that you've got a uniform voice there. And I think some of that could also be done in this area here. My background's with radar, and you've got a lot of academic groups and government groups that do a lot of INSAR processing. But we could also come up with basically one place where you go ahead and do all the basic processing, and then the academic groups will go ahead and still continue doing their own research in that area. But if we have a centralized processing, just do the first cut of some of these images. You can even say that with Landsat, being able to do kind of differences in time series where you got the Landsat image comes down. You just do a difference with it for the previous Landsat acquisition that had a decent amount of or low cloud cover, and to start generating these time series and be able to go ahead and at least have things done at a uniform level. Not all the scientific groups will agree with what that level is, but at least you got a starting point.
Well, I think I heard this morning that Google was interested in getting a hold of some data, and I think I just heard that we have some real challenges ahead of us with this, with the potential for debris flows, and I'm just wondering if this couldn't be a focus for. It would be a pilot probably, but maybe if people could focus a little bit on data acquisition and getting data in the format that people could look at it over the San Gabriel Mountains. I think you mentioned that the USGS already has some maps that they're working on, so is some LiDAR data already acquired?
Sufyan is a USGS scientist. She's produced all the debris flow maps for the 2003 firestorm, 2007, 2008, and 2007. She's currently working on this most recent one. And I think these are supposed to be approved and for public consumption later this week. So these will be the initial set that's going out there. USGS is collaborating with NOAA with basically using their SMART-R radar, which is typically out in Oklahoma chasing tornadoes during the summer months. In the winter, it'll be parked somewhere. Here, last year was parked off Santa Barbara to go ahead and work with the last year's Santa Barbara fire. And so, I lost my train of thought.
So you think that we're on the track to being able to do some real-time assessments of where we already know maybe
Yes.
where the high potential areas are for debris flows, but then we need, as somebody pointed out, we need the precipitation to follow up on with the precipitation information and some models to, if you will, predict the onset of a debris flow.
On Saturday, basically, as one of the lead scientists on submitting a proposal to senior USGS management. Basically, it's about a $7 million project to look at the effects of the station fire. And so that includes airborne LiDAR, ground-based LiDAR, multispectral, looking at the ecology. Basically, you've got some of the areas have been burned multiple times now, so that each time you burn it, you're going to have, you're changing the seed catalog. And so you're going to start getting more invasive species that come in. When you get more invasive species, what is their need? You're going to be rooting out the native species. We also talked about doing basically debris flow warning systems, and right now for this particular proposal, it didn't make the cut, but the discussion in the past has basically been putting geophones, basically used for earthquakes, out in areas where you likely have debris flows. And as soon as you basically start getting seismic shaking of a certain level, it would go ahead and trigger an alarm system. And so this has been, the USGS has been doing this on volcanoes for lahars. We're being able to go ahead and warn people downstream if something could go ahead and come along like this. So there's a lot of work that needs to be done. We just need to go ahead and get in a political climate where this type of research and stuff can be pushed forward. For the 2003 firestorm, we put together about a $5 million proposal to go ahead and do a lot of this integrated science. It fell through. Same thing with 2007, and I have no idea what's going to happen with this most recent one. We have actually collected airborne LiDAR, led a group where we collected LiDAR in some of the area that's actually was just recently burned, and we just took delivery of it last week. So we're actually going to have some pre-burn LiDAR data. We work with some other groups, possibly Forest Service, others, to go ahead and then collect some of the after-fire burn area. We'll be able to compare the bare earth models from the pre with basically the true bare earth models, which were basically collected after the fire. So there's a lot of good science that started coming out of this. Just being able to go ahead and free up the funds. And how many weeks before we get the next rainstorm?
Yeah, that's a good point. We don't have that much time, and thinking about the how things get done at NASA. You have to first, have the idea, identify the idea, then put it in a solicitation for proposals, then write the proposal, then have the proposal reviewed, and then get the proposal selected. And so, by that time, a lot of damage can be done. So.
Well, we've already had the 2003 firestorm. We had the 2007. We had the station fire. Do we have a pattern here?
Yeah. Well, I hope people, the funding agencies, are listening. So, okay. Any last thoughts from any of the panel members? Okay. With that, we can go to take a break and then reconvene for our last panel session. Thanks very much.